Hello everyone, how's everybody doing? I hope you're doing just fine. Got a couple issues to cover before we begin today. And one of them is that the rational scientific method in Facebook was finally shut down due to health reasons of the owner. And sorry to see him go. Anyways, as a result of that, I had to make some changes. Among them, that I need to have a place where people can ask questions, make comments, and what I'm doing with all that is, yeah, Mike, yeah, they shut it down. Rational scientific method is now dead. The only thing we have is the archives. That means you are able to download files and stuff of that nature. You can read what people wrote, that kind of thing. But essentially, RSM is, you know, reached its dead end. It served its purpose while it lasted. And so I had to make some changes, and among the changes, I need to, again, be able to communicate with people who want to communicate with me, and I'm going to do that through my Patreon page. Okay, so people who want to ask questions, who want to make comments, they can do so there. I'm going to be posting the transmissions over there, and so that's one issue. I'm sorry to see the good old monk go. Second issue is again we have a rational physics conference, the seventh one, and we're having that in Borås, Sweden. Here's the place, and anyone who wants to sign up, who wants to go, all you got to do is go to the Facebook page. You'll find seventh Rational Physics Conference there. Just look it up. You can also write to me at the Patreon site. Okay, so either way, you can sign up. Let us know that you're coming. Yeah, yeah, Mike. Yeah, the monk had to go, and I'm really sorry to see him go. But he's not completely dead. Don't kill him yet. He's gonna stick around. He's just got some health issues he's got to take care of. And Fat Fist also he disappeared. I don't know what happened to him. Maybe someone knows, but I certainly don't. And he was a strong, a guy who stood by his guns. Okay. What else do I have? Well, yeah, that's essentially it. Today I'm going to talk about a couple issues. One is the black hole that they not discovered, because we've been discovering black holes since the 1970s. That's not new news. That's old news. We've been discovering one every week. But the new issue is that starting 2017, I think it was, a project developed, the Event Horizon Collaboration. And what they claim they did is take pictures of a real black hole, the first picture of a real black hole. And yeah, that's the other issue I'm going to be talking about, is continuing with the ether and infinity and space, the nature of space, that kind of thing. But I'll do that in the second half. Let's go with the first half here. Here's a picture of the black hole. You probably all of you seen it somewhere. Here it is. That's what they published, and they claim that this black hole, what you're actually seeing, is not a black hole. They clarify that what you're staring at is the event horizon of a black hole. In other words, matter being sucked in through the event horizon. And yeah, if you were to publish and say that, hey, we took the first picture of an event horizon, nobody would know what they're talking about. It wouldn't have been news. Nobody would have paid attention to it. So they had to put the word black hole there. Black hole includes not only the event horizon, which is the region of influence of a black hole, allegedly, right? But it includes that center point, the zero-dimensional center of the black hole. And that's the tricky part there, because that's got infinite mass, I guess. I mean, they change their wording every time. Sometimes it's got infinite mass. Sometimes you have different masses of black holes. It's like it's an accumulation of mass. In other words, if a black hole gobbles up more matter out there, it's a factory that turns this matter into mass, gets rid of the body and keeps the soul, so to speak. And so, and so the mass is accumulated in a little tiny thing there. The more than tiny, it's zero-dimensional. There's nothing there, no size, no volume. Just gets getting massiver and massiver and massiver. There's ever more mass in there. And so supposedly, because of that, the event horizon of the black hole gets bigger and bigger and larger. The diameter of it gets bigger, and it could affect things farther and farther away. So that's the notion that these people have. One of the people who worked on the project, a lady, she's been for a couple years now, right? She's been groomed, I would think. That's what I suspect is happening here, because she's young, and so they say, hey, this is a good person to put your weight behind to prove things to people. If you find someone who can communicate with people well, and they're young especially, that always helps drive the message through. So that's a PR kind of tactic, right? And that's essentially what happened with this lady. And she has been talking about her involvement in the project. Her name is Katie Bowman. And she claims that she's not a physicist. She works on the project essentially by creating the algorithm that allowed them to piece together pictures taken or data taken from different parts of the earth by different observatories, and then they piece them together like she shows there. These are from her presentation in 2017, and she said what they've done is essentially take the images that and different types of data as well, brightness and so on, from different labs or different observatories, and they kind of map them together over time, and that's what she worked on. She worked on developing the algorithm. And yes, the issue with this lady is, again, that they use her, they're grooming her, probably for something big. Don't be surprised if she's one of the ones who wins the Nobel Prize together with her team. You know what I mean? They discovered LIGO. LIGO discovered, supposedly, two black holes that collided, right? And the collision generated gravity waves, allegedly. And these guys picked up and said, those were gravity waves. And they got a Nobel for that. So don't be surprised if, the photograph people, the paparazzi here, they get a Nobel as well for, taking the first picture ever of a black hole. I mean, it was predicted, and they bring Einstein behind there, and they drag him in there. Poor old Einstein never believed in black holes, but they say, oh, look, Einstein predicted. They have to put the word Einstein behind their PR campaign. And this lady is probably going to be in the same boat. She's going to be groomed, maybe gets a Nobel, and they're going to say, oh, the youngest person ever to win a Nobel, or something like that, because they need to really rub the black hole in. And the fact that they didn't say that they saw an event horizon, even though that's the name of the group, Event Horizon Collaboration Project, whatever, you know, they could have called it that, but they didn't. They know that people understand what a black hole is. They don't know what an event horizon is. Okay, so they took a picture, and her algorithm apparently put all the pieces together, the pieces of the puzzle together, and they came up with that big picture. Okay, one of the things that was missing, that I suspect that something is wrong, is, the jets. I mean, this thing is 55 million light years away, right? And see, you see jets in almost every picture they always put of a black hole. They have to put that jet in there because it looks so neat. You look at that first picture, or the last one, the one on the bottom right, and you can see the jet goes in both directions, okay? So you would think that things go into the black hole and go off to another universe, but apparently, from a physical point of view, it just seems like the rays just go. I mean, everybody who looks at this gets that idea that, especially in that first one, the flat disk there, that somehow that jet goes right through the black hole and out the other end. It's like if you're sewing a button and the thread goes from one side to the other. That's what it looks like. And, and then you wonder how they, assuming that's the idea you get from this picture, the question is, how do you reconcile that with, the idea that you go into a black hole and you end up in another universe? How do you go through a black hole and end up in a, I want to go through the wormhole. I don't want to go to the other side of the black hole and back into space again. In other words, this flat disk gives the idea that it's a two-dimensional disk of sorts. And, the jets go in either way. And likewise, maybe, matter falls into the black hole. And when it does, the question is, why would it go off to another universe? Maybe it comes out the other end as a jet. You see what I'm saying? So this is a problem that I see with these jets. And again, let me show you the picture here. Was it this one? No, it's where is it? Let me get it here. If I can find it, here it is. See, you can see where the jets. I mean, if we can see jets in these pictures so well, how come we can't see a jet here? If matter is falling in there, where are the jets coming out? I mean, is this a two-way membrane where stuff falls in and the jets come out of the same hole? We got a little bit of problem that needs to be clarified as a minimum by proponents of black holes. Okay, that's one issue that I wanted to point out. The other issue is, this is how a black hole is formed, okay? And we have a problem there because, everybody has a different idea, or, the experts are putting out different notions of what a black hole is. NASA says that a black hole is a great amount of matter packed into a very small area. Small area. They're not saying zero-dimensional, they're saying small, okay? And says, think of a star 10 times more massive than the sun, squeezed into a sphere. We're talking about a sphere, right? Hopefully a sphere is not zero-dimensional. Approximately the diameter of New York City. Well, that's a pretty big sphere. Imagine if you went to New York City and found a sphere, and you went all around it. Well, it was maybe on a cosmic scale, it's a small sphere, but from your point of view, it's a pretty big sphere. It's more than zero-dimensional. That's my point, okay? And it says the gravity is so strong because matter has been squeezed into a tiny space. Again, tiny, not zero-dimensional. And scientists think the smallest black holes are as small as just one atom. Well, an atom, I guess, is not zero-dimensional either. But that's not what the Max Planck Institute, the people who worked on this Event Horizon Collaboration Project, Max Planck was very heavily involved in that. It says a black hole is not a tangible object, not a tangible object, but a region in space that draws in matter from its surroundings. Okay, black holes themselves are not solid objects, but rather a region of space with very special properties. And then you have the people, you know, at the university saying that matter is crushed out of existence. Okay, all matter is crushed out of existence in a black hole. There's nothing there, nothing left in there, no matter, no length, width, and height. So the question is, what are we talking about? We're saying that the body of the deceased, disappeared, completely disintegrated, vanished, and what's left is the soul, the spirit that goes off to heaven. That's essentially, you can say that religious people have taken over physics. Traditional religionists, they come from these backgrounds. Their mother and father, maybe their grandfathers, they believed in religion, in the traditional religion, mostly Christian, I would suppose. And these people say, oh no, I'm an atheist. I don't believe in such nonsense. And it turns out they believe in bigger nonsense. They believe in black holes. They believe that matter in this factory they call a black hole, a singularity, surrounded by an event horizon or region of influence. Turns out that this entity, I don't even know if to call it an entity. I mean, it's what is a black hole? These guys say it's an object. These guys say it's a mathematical concept, just a region. Well, whatever it is, it's a factory that crushes all matter out of existence, and it just has mass. And what is mass? Mass is a mathematical concept. Can't do anything with mass. I can't throw mass against the wall because I can't even grab it in my hand. I mean, I can throw a brick against the wall. I can't throw mass against the wall. What these people are saying is, we lost length, width, and height. There's no object there, no ball, no brick, no tree, no rock, nothing. Only the weight, so to speak. It's like, you crush the elephant out of existence and his 5 tons are still there. That's what they're saying a black hole is. And of course, the next issue is that they'll tell you, oh, by the way, we have no idea what a black hole is. No kidding. No kidding. I mean, you either define it if it's a mathematical concept, or if it's a physical object, if it's a bowling ball, well, you point to it. You say, oh, that's a black hole. And all I have to do is just look and say, okay, I see what you're referring to every time you mention the term black hole. It's that black thing you're pointing to there. So it's either that they point to a shape and I can see that shape and say, okay, I identified the term black hole with that ball that you're pointing to, or it's an abstract concept, a region of space, supposedly. Think of it as a hole in space. So we're talking about an entrance, an opening in space, whatever sense that makes to you. It's like we ripped a little bit of space, and just, Bugs Bunny or Elmer Fudd stuck his head through there and say, that's all, folks. That's what a black hole is. So which is it? Is it the flat 2-dimensional hole that opening in space, or is it a 3-dimensional ball that's floating in 3-dimensional cosmic ocean, in a cosmic ocean? And this is what they have never clarified. And yeah, here I have proof, evidence to convince you. Okay, here we have Mr. Stephen Hawking. And he puts this in his book, A Brief History of Time, and he says the following. He says, talking about Chandrasekhar, who was the Indian fellow who later is going to win the Nobel Prize for this. And Chandrasekhar in the early part of the 19th century, right? Just after, 20th century, just shortly after Schwarzschild discovered, or the equations for the black hole. Chandrasekhar says, that you can have so much mass that if there's a star bigger than our sun, much bigger than our sun, it can be crushed right out of existence. And of course, the mass still remains in there. That's what Chandrasekhar was saying. That's what Schwarzschild was saying, and everybody else in those days, essentially. Maybe Arthur Eddington was the only guy who didn't believe in black holes at the time. Today, everybody believes in them. But what Hawking says is Chandrasekhar realized that there is a limit to the repulsion that the exclusion principle can provide. When the star got sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. In other words, here you have a massive star, a massive object, and it's pulling matter towards its center, right? This is the star that's collapsing gravitationally upon itself, upon its center. It's being squeezed inwards, right, towards its center. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. Eddington thought it was simply not possible that a star could collapse to a point. Okay, but so he was looking at it the physical point of view, where Chandrasekhar was saying, well, mathematically it's correct. Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. But that's what Chandrasekhar was proposing, that a star can shrink to zero size. And what was left was the mass. The mass did not go to zip. The mass just stayed there. That's the issue. You got rid of the elephant, but the mass remained. That's the trick. That's the magic of this. And Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. Okay, so what's the issue? Well, the issue is that you got to understand what's happening here from a physical point of view. That's all we're interested in here. We're not interested in the math. We're saying that, you take any object, take a rock, okay? Let's assume you had the way of crushing it from every direction, right? All around it. You squeeze it inwards, 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 inwards. Well, for sure you're going to crush it. It's going to break, but you don't allow any piece to leave the rock, okay? So you're able to control all the matter, all the atoms that comprise the rock. So far, so good? So you're squeezing this rock, right? And just squeezing it inwards, inwards. Essentially, you're squeezing atoms against atoms, right? Because, atoms in a rock, if you were to had the eyes of God, you would be able to go in there and you would see that there's a distance between them. And what we're saying is now you're breaking that distance and you're essentially getting those atoms closer and closer and closer together. And at some point, you're going to be squashing atom against atom, right? And you're making this ball from this big rock. You're making a little ball of just pure atoms, almost, right? And you keep squashing and squishing and crunching all that. And you continue and continue and continue until there's no structure left. There's no length within height. There's no matter left. But they don't say that the soul dies with the body. They say the soul survives the body. This is the trick. The trick is the mass survives the crunching, the disintegration of the matter that comprised it, of the atoms that comprised it. That's what these people are saying. So this is a mathematical trick, just a mathematical trick. They're saying, look, we got rid of matter, but the mass remains. And the funny thing, as I showed in Mexico, or argued in Mexico, in Acapulco, that's a circular argument, because mass is a measure of the quantity of matter. That's the definition of mass, or the notion people have of mass. It's the quantity of matter, or a measure of the quantity of matter. Now we got rid of matter, and these people are saying matter's gone. There's no more matter. What remains is mass. How can that possibly be if the definition of mass is the quantity of matter, or a measure of quantity of matter, however way you want to phrase it. In other words, what these people are saying is you can have mass without matter. But that violates the definition. And of course, what they're probably going to throw at me is saying, oh, you're just doing semantics. Okay, I give up, white flag, you know. So this is the issue. The issue is, these people crushing matter out of existence, and they're leaving the mass. And when you look up the word mass, it's the quantity of matter. There is no more matter, but there's still mass. So now we have to have a new definition. Before they give them the Nobel to this girl here, they should go out there and at least take the trouble of defining the word mass, redefining it now, because I don't know how they're going to define mass, if there is no matter. Anyways, okay, and this is the main problem with the black hole that I see. And again, as you can see, you either put the two-dimensional entrance on the side of a cube of space. In other words, you have to be on the surface of space in order to put that spot there, that two-dimensional entrance. It's got to be on the surface. And that contrasts again against the bowling ball. If a black hole is a bowling ball, a three-dimensional bowling ball, which is what I really don't know which of the two they claim to have taken a picture of. I mean, maybe they took a picture of the two-dimensional hole, maybe they took a picture of the three-dimensional ball. Which is it? This is what we need for them to clarify. So if you run against an expert, someone who challenges you, or you want to challenge him, well, this is the way you challenge him. You say, look, we either have, a spot on the side of a cube of space, a volume of space. It's got to be on the surface. Remember, these people took a picture head on, just like you see in that left picture. If you take a picture of a black hole head on and you see a hole there, you're looking at the surface of space. You're not looking at the inside of space. You're not looking at the volume of the cosmic ocean. You're not looking at the ocean. You're not inside the ocean. You're on the surface of the ocean. That's a top view, in other words. That's a view from the sky that you're seeing on the left side. The one on the right, on the other hand, that's a bowling ball stuck in a volume. No problem there. We can all understand it. But then we have, again, that problem with the jets a little bit, because here you can see that the gravity points towards the center of the black hole, which is the singularity. That's what you see on the right-hand side. On the other side, the singularity is just an entrance to another universe, which is that yellow line which indicates the flow of gravity. In other words, gravity goes into the hole and just out to some indefinite tunnel, wormhole, that takes you to another universe. So these two are two different notions of what these people are putting out for the black hole. Physical notion. We're not talking about the math here. We're just saying, please explain it in physical terms. Which of the two are you presenting? Are you saying that you took a picture of the one on the left or the one on the right? Did you take a picture of a two-dimensional ball or a two-dimensional hole or a three-dimensional ball? Does gravity flow through a wormhole to another universe? Or does gravity flow towards the center of the ball to the singularity? And so this is the issue. This is the problem that we have with the black hole. And I doubt very much that they'll ever solve it. Okay, so these black hole theorists, well, I don't know. It's up to you if you want to believe them. You might as well believe in spirits. I'm not sure what to tell you. There's nothing there. And as far as I'm concerned, this is just a PR campaign. The fact that they put the girl there and they've been grooming her for at least 2 years. You'll see videos of her all the way to 2017 announcing that they're going to be taking a picture, a guaranteed picture of a black hole. Now they obtained it. What's next? The Nobel Prize. That's all I can think of. And well, I'll bet everyone who comes to Bora, Sweden, I'll bet you a beer. Okay, that this gal, well, I don't know about the gal, but I think the team is going to earn a gold medal. It just seems to me that this girl being young and she's been groomed and she's been talking, she's done a couple TED Talks. I think she's only 28 or 29 years old. And I have to believe that she's going to be one of the recipients of the what is it, of the Nobel Prize. The only reason I think that is that they've been grooming her, and she was beaten up by some people, who laughed at her, saying, what's this woman doing, calculating all this stuff, etc. Maybe she should be in the kitchen washing dishes or something. So they gave him a lot. They gave her a lot of hell. But I'm almost sure they're gonna use this girl one way or another, and it's gonna be whatever they do. It's gonna be for PR. Okay. And that doesn't take away from her work as a programmer. As she developed an algorithm, fine, no one takes that away from her. But that's different than using her as a propaganda piece to shove black holes down your throat. Again, the only thing they need to do with a black hole is define the term, if it's a concept, if it's an abstract mathematical concept, or point to it, draw it, and point to it and say that's a black hole, a black ball, almost certainly. And first they have to distinguish between them. Then they have to tell us, whether gravity flows all the way to another universe through a wormhole. In other words, is the singularity just an entrance to another universe, physical entrance to another universe? Because they do talk about wormholes, right? As if they were for real and they connect universes, okay? So is that just an entrance into a tunnel that takes you to another universe? Or is that just, the gravity goes down to the singularity? Which of the two is it? So they have to clarify those issues. Okay, enough for the black hole. Again, bring up questions at the Patreon page if you want me to look at the questions. Let's go back to where we were, which is we were trying to deal with our universe. It is related to the black hole anyways, right? Because, what is our universe? I mean, can you make a hole through space? Well, if space is a brick wall, yeah, you can make, or I guess even an ocean. You perforate the ocean. I mean, after all, that's what a fish does, right? Just swims through the ocean. It's just pushing water aside as the fish moves, right? So you could say, yeah, you can perforate an ocean in that sense. Is that what we can do with space? I mean, when the astronauts go out there, do they scratch their elbows against space? And the answer is, is there any resistance in space to their flow? Are there hundreds of particles or fields or of energy getting in their way? Do they have to swim through all this stuff to get through it? Or do they just encounter no friction whatsoever? What's your gut feeling? I'll tell you mine. Space is nothing. But some people believe it's something, and that's where we started. Some people identify it with the ether. They have this idea of the ether, and the ether has a couple notions out there. One is the notion that the ether is made out of particles, and in fact, that is I would say it's the only notion. Some people want to say waves, but waves of what? Of particles. So in the end, whether you deal with wave theorists or particle theorists, like I showed with the debate between Newton and Huygens, ether is taken to be a bunch of particles. And then the question comes, is the ether the same thing as space, or the space encapsulate or enclose or hold all these particles? Is space a different medium than the particles, or are the particles space? Are they the same thing? And of course, they never answer that question. No one has been able to answer that question. They give me a lot of nonsense because they don't understand the question. People who tried to answer it, they don't understand the question. And the question is, what surrounds one ball of ether? That's all I want to know. Well, what's outside of that ball of ether? What gives it shape? Why doesn't the shape continue and become a single block of space made of a single piece. That's what you would think. If there's no space, no nothing separating one ball from another, or one cube from another, if you're into cubes, if there's no separation there, how can you tell that there's a little cube, a little ball? The only way you know that there's a ball there is because it stops at a surface and then something else continues. Well, what contoured? What encapsulated that ball or that cube to separate it from the next one? That's what you got to come up with. You got to tell me what that thingy is. And of course, no one can do that. No one can do that because, again, some people think that space is the balls, and others think that space is the container of the ball. So they're two separate things, okay? But in either case, then the issue comes, the question comes is whether that space extends forever, indefinitely, infinitely, and whether the balls, or cubes, whatever you think the space is made of, whether those are infinite. And if they're not infinite, what encapsulates it? And if they're infinite, what do you mean by that? How can there be an infinite object? What sense does that make? You gotta solve that problem before you tell me your theory. I don't want to listen to your theory unless you can solve that problem. It's called the hypothesis. And first we deal with hypothesis before we get to the theories. People don't like that because they say, well, you're playing around with language, you're doing semantics. This is physics. It's known as physics. You need to tell me what space is. You need to tell me what the particles are, what encapsulates them. And that's the issue we have today. When people like Lawrence Krauss tells you a universe from nothing, he writes a book, a universe from nothing. And then he said, well, it's not really nothing. It's a bunch of fields or particles or virtual particles, pop in from the void, or it's a bunch of energy. And they'll use these words like if they knew what they're talking about. There is no physical object called a field. There's no object called an energy, no object called a mass. All those words are concepts, from mathematics. So no, I need pictures. I need drawings. I need for you to grab a crayon. I need for you to grab watercolors, if you like watercolors, chalk, board, and start drawing. I need to see a picture. No picture, you have no theory. Not a physical theory, at least. Not anything that we can use in physics. We need pictures, pretty pictures, okay? Okay, so what happened? Well, we went back in time. We looked at the Greeks, right, a couple of weeks ago, and we found out that they had the same problem we have today. And nothing changed much for the next 1,600 years or 1,800 years until we get to the 17th century. Some people started looking at the ether because of light. They're trying to figure out light, among other things. They had this fight eventually between Newton and Huygens. And Huygens, people think today that these guys were fighting because one guy was in favor of waves, and the other one in favor of particles. And that's not true. Absolutely not true. Both Newton and Huygens, wave theorists, so-called wave theorists, they all believed the ether was made of particles. They all believed in particles, all of them. I showed you in the book that Huygens wrote, he talks about particles, the ether made of particles. So they were all particle men. The issue was whether the particles were waving up and down or whether the particles were somehow going straight. In other words, was light just a particle going straight like a bullet? Or was the ether, full of particles just undulating? That was the issue. And Newton said, light goes straight, and I can't imagine how it can wave up and down, first of all, because light travels straight, he said. And then the other issue was that, if light undulated up and down, how is it that a transverse wave can travel through a fluid? If this is a fluid thing that moves up and down, undulates, you can't have a transverse wave, as we eventually found out. But that's the notion Newton had in mind. And, his notion, his objection, lasted all the way to the 19th century. Now, there was another development in the 17th century, and it was Roemer's discovery that light does have a speed. And he determined this by looking at the Earth at the two different 6 months apart, you know. And he was looking at the moons of Jupiter go past behind Jupiter. And one of the things that really got him was he said, you know, we expect this moon to come out in such and such time, and it turns out that the moon took a little more time than usual. And he eventually figured out that the difference was due to the speed of light getting to his eyes because he was farther away. He was on the other side of the sun by that time. And so he said, look, the speed of light is not like Galileo and like Descartes, Rene Descartes had said. Speed of light is finite. The other two guys believed it was infinite. Both of them died before 1650. I think Descartes died 1654, something like that, mid-century. And both of them died believing that the speed of light was infinite. It was Romer who's going to show that no, the speed of light does is finite. You know, there is a speed to light, and it's Huygens who's going to calculate more or less. He just gave it a ballpark figure of how fast the speed of light was. The guy who's going to improve on that next century, beginning of the first quarter of the 18th century, would be James Bradley. He does that by showing parallax, also known as aberration, essentially. He looks at a star as the Earth is moving, and he calculates the angle between them, and essentially does a calculation, says, you know, the speed of light is not only finite, he confirms that, but he approaches or approximates the speed of light to a higher accuracy than Huygens had figured it out. Okay, all we have is speed so far. We still don't know what light is to this time. In fact, people on the authority of Newton believe that light was just a bunch of particles, and that's what Al Hazen had figured out. Also, Arab guy in the in the Arab Spring of those days. The Arabic world was expanding. It had a lot of scholars. 10th, 11th, 12th centuries. They were pretty strong on science, you could say. They were doing research. They had all these scholars. And Al Hazen was the first guy who says, no, light is not like Euclid and the Greeks believed, or so many of them believed, that comes from out of the eye and goes to the object. No, it comes from the object to the eye. And he was thinking of particles. And Newton essentially goes with that idea that light is just particles coming from an object to your eye, and this lasts all the way to the beginning of the 19th century. And it is at the dawn of the 19th century we have Thomas Young and Augustin Fresnel, and Young in England and Fresnel in France. And they come up, especially with this slit experiment, they figure out, both of them, that light is some kind of wave phenomenon. Young was really more concerned about colors. He started doing some experiments on colors following Newton, and he essentially debunks Newton. He says, look, Newton was wrong. And that was a big issue in those days. It's like saying today that Einstein is wrong. You know, if you prove out there that Einstein is wrong, you're going to have a lot of people down your neck. And that's the situation with Thomas Young. A lot of people didn't like that he was tearing Newton to pieces. And that's confirmed finally in 1816 by Fresnel, who writes a paper showing that the slit experiment can better be explained with waves. And it's not until 5 years later in 1821 that he needs the wave more than ever before to explain polarization. Okay, so when Augustin Fresnel shows that polarization can be explained with transverse waves, light takes on a brand new meaning. At that point, people start looking at, forget about Newton completely, and the 19th century becomes a century of waves. It's just everybody trying to explain the wave. What is Fresnel talking about? Well, he had in mind something similar to this. Okay, He didn't specify it especially like that, but he gave the notion that light has to be like a double transverse wave of some kind, because that's how he explains his picket fence mechanism. He says, light has a vertical and a horizontal component. Let's assume that. Okay, fine. And then the calc-spar slabs, the vertical one blocks the horizontal component of light, and the other one extinguishes the beam altogether because what went through was the vertical component of light. So that's essentially what he was saying. Now notice a problem with this little wave that we still use today, and that's that it only goes one way. Okay, that's one of my objections to this. Also, the objection applies or can be extrapolated to particles. Particles and waves, they come out of the atom, they go in one direction. That's already fatal to wave and particle theorists. There's no way they're going to ever get around that. And that's why they can't explain light to this day, because you can't explain light with waves or with particles, assuming that waves, wave is a physical object. It turns out a wave is not a physical object, it's a verb. So you can't do physics with verbs. So, the transverse wave, even longitudinal waves for that matter, you can get rid of them completely. You got to tell me what the object is, what the mediator is. In the case of particle, well, particle is an object if you're talking about corpuscles. If you're talking about, I don't know, baseballs, that's fine. Grains of sand, that's good. You're talking about cubes, Rubik cubes, just going, okay, that's acceptable. You can say light is mediated by Rubik cubes. Okay, that's acceptable. Now you explained your theory. But you can't say light is mediated by waves, because there is no physical object called a wave. Wave is a verb. Wave is what an object does. And these people knew this. This is the interesting part. I showed last time, who was it? George Stokes here. And he was aware that there's a problem. In fact, he writes this paper in 1845, and it's going to be important because Fitzgerald and Lawrence, they're going to pick up on Stokes later on in the century, and they're going to use Stokes' paper here, 1845, as a reference, okay? And what does Stokes say? And Stokes is important because he was the head of the Cambridge Department of Physics, essentially. He was the chair. He had Newton's chair, the Lucasian chair, I don't know how they pronounce it over there. He was on that chair for 54 years. Now that's a place to sit your butt on for 54 years. It must have been flat. But he's the guy who's been the longest Lucasian professor. Okay, and he said, the more particular explanation of the cause of aberration usually given does not apply to the theory of undulations, unless we make the rather startling hypothesis that the luminiferous ether passes freely through the sides of the telescope and through the earth itself. The undulatory theory of light, however, explains so simply and so beautifully the most complicated phenomena that we are naturally led to regard aberration as a phenomenon unexplained by it, but not incompatible with it. Okay, he's essentially trying to figure out, how he's going to fit this transverse wave that Fennel discovers in the 1820s. And here's in the 1840s, and they're trying to figure out light, gravity, not so much gravity, but they were trying to figure out light, magnetism, electricity, those things. And so he's saying, ether, it's the vibration of the ether. And that's important because, later on Michelson and Morley in the 1880s are going to try to figure out if there is an ether. And that's a long story, and there's different very heated opinions on what Michelson and Morley really discovered. Okay, and I'm going to go over that. But today we got to get to this other fellow, and that's Mr. Maxwell. Okay, so Maxwell comes up, and he comes up with 4 equations. Okay, and you say, oh my God, who can understand all that nonsense? Look at all those symbols. So people immediately get turned off, and they say, I have no idea what all that is. Well, let's understand it from a physical perspective, okay? Let's just look at the physical part. Let's look at that first equation, which is Gauss's law, Okay, Gauss was a mathematician. Okay, and he was a pretty good mathematician, but apparently he stole that secret from Lagrange. He was Giuseppe Lagrange. He became a French citizen, and he was known as Joseph Lagrange. And Lagrange, for 40 years before Gauss, had already figured out that electricity comes out of charges. And how can we phrase this? We can say that the static electric field points away from positive charges and towards negative charges. They had already discovered that. And what Maxwell does is he puts this in a mathematical form. It's one of his 4 equations, one of his most famous equations. But that's essentially what the equation says, that, the flow of charges, whatever charges are, goes from positive to negative. That's what the equation says. Okay, in fact, it's important to know that, some of these discoveries were already hanging around, before some of these people got to them. Like, here I have another version of that, and that's Coulomb's, let's see if I can get it here, Coulomb's experiment. He did this also in the 18th century. And what Coulomb does, he realized that if he charges up a little electrode, he can put this thing back in there inside the that little enclosure, and he's going to repel one of the little balls there, you can see, and that's his first reading, the red mark. Then he goes in there, he charges it again, but this time he releases some of that charge, and the second time it doesn't push the little yellow ball there as far. So the first time he pushes it far away, second time he pushes it less far away, and he realizes that there's a relationship between, the strength of the field, that he can kind of store the charge and be able to diminish it and augment it. And this is the equation that eventually comes out. The 2 charges divided by the distance squared between them, the radius squared. Okay, so Maxwell goes in there and he puts his first equation. The second equation has to do with also with Gauss, but it's got to do with magnetism. And essentially, he says that there's no such thing as a monopole. Okay? You always need 2 poles, unlike in electricity, where you can have a single pole, a negative pole, I guess, standing alone, and this field surrounded it, going all the way to the edges of space-time, I suppose, because they say it's infinite. The magnetic monopoles, there's no such thing as a magnetic monopole. You need 2 of them. You need a positive and negative. And that's essentially what the second equation analyzes, or that's what it stands for in physical terms, okay? That's what Maxwell was trying to get across. Okay, third equation. Third equation says that, comes from Faraday, and says that if you take a magnet and put it inside a coil, okay, you induce a current through the coil. The coil has to be, a live coil, right? But if you take a magnet, put it inside the coil, you will increase the current. And the fourth equation is more or less along those lines, but in reverse, you could say. Fourth equation, Maxwell equation, says the opposite. Says, look, if you have a current, you will notice that you will have a magnetic field going around it. In other words, a flow of electrons or a flow of electric current, whatever that was, because they didn't know, right? Whatever that was, it generates, for some reason, it generates a magnetic field around it. And this came from something that already happened in the early 1820s, I think it was in 1820, where Ørsted accidentally discovers this in a lab. Ampere got wind of that, And he started experimenting that same week, or I think the next day, when he learned about it in France. And he realized not only that Orsted was correct, but he realized something else, which is quite interesting. Let's see if I can find it here. Here it is. I think it's this one. Yeah, he realized that if you have two wires and you have current going in opposite direction, like in this case, they repel, and if the current goes in the same direction, the two wires will attract each other. So he's the first guy to notice this effect. He can't explain it. He just says, "Oh, look what I found! What I discovered." And essentially, these are the things that Maxwell is going to put in those four equations. That's what he's famous for. Okay, and not much more than that from a physical point of view. Again, I'm not interested in the equations. We're not going to analyze equations here because they have nothing to do with physics. We want to know if they want to scribble things on the board, fine, no problem. I want to know what it means physically, and that's what it meant physically. You're talking about electric charges, whether they're infinite or not, whether you have two poles or one pole. These are things that concern people in the 19th century. You're concerned about whether a magnetic field can live with a monopole, and you have just one monopole in a single pole, a north pole in a magnet, and the field all around it. They were concerned about magnets creating an electric field, or electric field creating a magnetic field, and that's what Maxwell's equation essentially address. Okay, and I'll go a little more deeper in those issues next time around, but I just want you to know what was going on in the 19th century. And what was going on is these people were investigating these issues. A lot of this had to do, by the way, with developing technology. Technology was working very closely with some of these people, with mathematicians. They were trying to say, "Oh, what did you discover in the lab? What did you discover in your on your blackboard?" And these people would come around, and someone would pick up on that and say, "Oh, maybe I can do this with it." And that's how they got the ideas for developing technology. And so one of the unfortunate things about this whole thing is people slowly lost science. They forgot about science altogether, about explaining mechanisms. And they said, "Look, what is it useful for?" And the guy says, "Well, let me describe it mathematically." And the guy described it mathematically, and others would understand those symbols, and they say, "Oh, now we can describe how gravity behaves, how electricity behaves, how magnetism behaves, how light behaves." They still hadn't gotten to the atom. And then other people, say, "Okay, let's see how I can use this information to develop some technology." And so it was a debate, not a debate, a discussion, a dialogue between mathematicians and technologists. The scientists were never invited to well, I'm sure a lot of people like Faraday and Maxwell pondered trying to give a physical interpretation to these things, but they were more concerned about describing, not about explaining. And that's what people today still don't understand, that Maxwell was not a scientist. He was not a scientist. A scientist is someone who explains. Faraday tried to explain. He couldn't explain. Maxwell did not explain. He just described. So you can give him a Nobel Prize if you want for describing, but you can't give him a single penny. He's a bum as far as science is concerned. He was not a scientist. Scientist is someone who explains a mechanism. That's not what Maxwell did. Maxwell, what he did, describe what he couldn't see. He said, "This is the way it behaves." And that's what we have today. Today we have descriptions, mathematical descriptions. We have technology and no science, no understanding. And that's what this site is about. We'll see you on, Wednesday? We'll see you then. Same time, same station. Bye-bye.